Okay, so let's make a start with this hands-on session. If you copy and paste the link that I've posted in the chat into your browser, you'll be able to navigate to the project that we're going to use. So once you've followed that link, you should be able to see the project shown in your browser. And the button we're looking for is in the top right-hand side here. What we're going to do is copy this project to create a new project that you can edit and follow along with. So if you click the copy button, we can then just change the copy here to your name or something else. So I'm going to set this as Steve and create a copy for this one. So this will launch the project that we're now going to use for this session. In the left-hand side, you can see the different milestones that we're going to use. And the first thing that we're going to do is go to the geometries at the top left-hand side of the tree. So I'll just click on there and give it a moment for everyone to catch up, just in case some people's browsers are a bit slower. Okay, so once you've got the project loaded, in the left-hand side, go to the geometries and click on the restaurant 20 degrees geometry at the top. Just before we get going, I'll go through some basic tips on how to navigate the model. If you left click and drag the mouse cursor, it will rotate the model. If you have an external mouse, you can use the scroll wheel to zoom in and out. And if you press the control button on the keyboard and then left mouse click, you can pan the geometry across the screen. And then on the right click context, we can do various things like hide faces. So we're going to use these different selection methods to navigate through the model during this session. So you can see here we have the model of the restaurant, classroom or office, and we've got 4 tables laid out with 4 people sat at each table. We've got the open windows on this side, and we have 7 lights on the ceiling, and in the center we've got an outlet and 4 diffuser inlets for the HVAC system. So this is the geometry that we're going to use. From here, if you wanted to create a simulation from a geometry that you have imported, you can just click Create Simulation, and then this shows you the different simulations that we can set up. Today, we're going to be doing a convective heat transfer simulation. And this allows us to simulate the heat transfer in a fluid, in this case the air, by natural or forced convection. So if you click Create Simulation, this will then create a new simulation in the tree. And it's assigned the geometry because we selected the geometry to create the simulation. So that completes the milestone 0. And now if you click to milestone 1 in the tree structure, we'll go through and assign the materials. So what we're going to be doing is going through the tree, and we're looking to get a green tick on everything, but we're going to do this gradually using the milestones so that you can follow along and get an idea of how we would do each stage of the setup. So the first thing that we've got here is the model, and I'm just going to check that gravity is assigned on the correct axis. So we can see here that Z is indeed the axis for gravity in this geometry, and it is in the negative direction. So we've got negative 9.81 in the correct direction, so that's fine. And then the next thing we're going to do is assign a material from the library in SimScale. And for this simulation, I'm going to apply air as our material, and it automatically selects the volume that we've got here as part 1. So that's fine. I'm going to tick OK to that to save that. So now milestone 1 is also complete. We've assigned the geometry and we've also assigned our material. The next step here is to go to milestone 2 in the tree structure. And in milestone 2, we're going to set up the boundary conditions. So you can see we've followed through the things from the previous milestone. So we've got the geometry assigned and we've got the materials assigned. And now we're going to start setting up the boundary conditions for this simulation. I'm going to start by assigning a wall boundary condition to the external walls. And to do that, we can select all of the external wall faces. And then set these walls up so that they have the correct boundary conditions. So here we're going to say that they're no slip, wall function, and we're going to say that the temperature type is a external wall heat flux with a derived heat flux and a heat transfer coefficient of 25. And the ambient temperature is 15 degrees Celsius. We'll say that the wall thermal is a specific conductance wall thermal at 0.133 watts per Kelvin meter squared with an initial boundary temperature of 20 degrees. We're going to say that they are opaque with a emissivity of 0.96. And there we've selected all of the faces. So now that we've selected them, it assigns them to all of the faces. So I'll just leave that on the screen for a moment so that you can follow along with what I've done for the external walls. And then as the next boundary condition we're going to set up, we'll set up the diffuser inlets. So for the diffuser inlets, we're going to do a velocity inlet. And we can go through and select the uppermost faces of those diffuser inlets. And we're going to assign a flow rate to these. We're going to assign a volumetric flow rate for the flow volume that the HVAC system is applying. And this is a flow per diffuser inlet. So we're going to assign 0.03 meters cubed per second to each diffuser. So that will be 0.12 meters cubed per second for all of the diffusers. We're going to say that the HVAC temperature is 15 degrees Celsius, and we'll leave the other settings as they are. Again, I'll just leave that there for a moment so that you can see the settings that have been used. Okay, so the next boundary condition I'm going to set up is another velocity inlet for the windows. So we can spin the model over and select the open portion of the windows for where the air is going to come in. And we're going to assign a flow rate and again a volumetric flow rate to these windows. And per window, we're going to assign 0.048 meters cubed per second. And we're going to say that the outside temperature is 15 degrees Celsius, the same temperature as the HVAC air. We can obviously rename these if we've got more than one velocity inlet. So we'll call that one window inlets. And let's call the first one diffuser inlets. Okay, so the other boundary condition I'm going to show you how to define here is the outlet. So for the outlet, we're actually going to assign a natural convection inlet outlet. And this will naturally balance out the velocity inlets coming in from the diffusers and the windows to be the outlet at the top. So we'll say it's natural convection with an ambient of 15 degrees Celsius, and that sets up our outlet. Obviously, there's some more boundary conditions to set up here. We would want to set up the heat generated by the lights and also the people, the external floor and ceiling. But in the interest of time in this session, I'm just going to do those boundary conditions with you. And now if we move on to milestone 3, we can see all of those boundary conditions already assigned. So we've got the occupants, and here we've got the occupants as a flux heat source. We have the external walls, the ceiling, and the floor with their specific conductance values. We have the windows on the non-opening side, the lights as a power heat source, the diffuser inlets, the natural convection outlet in the middle, the window frames, the doors, the windows on the opposite opening side, and the window inlets. So you can see in the template how you can go through and set all of those up. Okay, so the next thing that we're going to do now in milestone 3 is set up the passive scaler for measuring the mean age of the air. So to do that, we need to go back to the simulation. So you click on milestone 3, and here we can see some settings to do with the actual simulation. Time dependency and also passive species. So we're going to now include one passive species into our simulation. Okay, so now that we've included a passive species, we'll be able to calculate the local mean age of air. And to set this up, we go to the advanced concepts in the left-hand tree, and we're going to add a passive scalar source. So here we're going to add a volumetric passive scalar source to the entire volume. So we can select part 1 as the volume here. So that's the entire fluid volume. And we're going to be assigning a volumetric passive scalar. And the flux here that we're going to assign is 1 meter cubed per second. The next thing we have to do to be able to measure the mean age of air at the exit is to set up a result control. So if we click the plus on result control, we're going to add a surface data calculation, and we're going to make it an area average. So here we select the outlet face, and we're going to do a area average. So we can call this outlet average and set up a area average with the right control at each time step. So this will write out at the exit our data per time step. Okay, so that's everything set up for the passive scalar. The only other thing to check is what the initial conditions are. So we just check that for the passive scalar, we have a global of 0 under the initial conditions. So that's ready to go. If you go on now to milestone 4, where we already have the passive scalar set up. Okay, so in milestone 4 now, we're going to set up the thermal comfort. And in order to measure the thermal comfort, we just have to add something under result control. So we have to add a field calculation, and from there we can select thermal comfort parameters. So we can select the thermal comfort field calculation, and then there's some variables to assign: the clothing coefficient, the metabolic rate, and the relative air humidity. So we're going to assign 0.5 for the clothing coefficient, 1 for the metabolic rate, and 65 for the relative air humidity. So that's the thermal comfort field calculation set up, and we can then move on to milestone 5. So milestone 5 has the thermal comfort set up, and in milestone 5 we're now going to check the mesh. So in the tree structure here you can see the mesh. If you click the mesh, it will load the mesh settings. Now on this milestone we already have a mesh assigned, but we can see that it used the standard algorithm with automatic sizing and a fineness level of 5. We used the standard settings for the automatic boundary layers with 3 boundary layers and an overall relative thickness of 0.4 and a growth rate of 1.5. We're using the physics-based meshing and hex element core. And this mesh was generated in 14 minutes and it used about 3.7 core hours. So we're going to go ahead and use this mesh, but please feel free to come back to this simulation and rerun a different mesh if you want to try different finenesses. Okay, so let's now go on to milestone 6. In milestone 6 now, we're going to set up the first simulation run. So we've got all of our boundary conditions and our model set up. We've got our mesh. So here we can start a simulation run. And for this simulation run, I'm going to give it the name CHT for convective heat transfer, windows open, 20 degrees. So give it any name you like, and then you can start off a simulation run. So that's now computing our solution, and it's started the simulation. If you go now to milestone 7, we're going to start off a second simulation run. So we've started our first one, and now we're going to do a second simulation with an alternative geometry. So if you go to the geometry here, just under the milestone, we're going to select the alternative 40 degrees window opening. So you can see our geometry changes now to the window that's open to a greater degree. And we get a warning that we might lose some things. However, in this circumstance, we've used a parasolid and we've got associativity between the two different CADs. So all of our boundary conditions are still assigned, but we've swapped out our geometry. So now we can just run off another simulation using different geometry. So let's start off another simulation run. Again, I'm going to call it CHT, windows open, 40 degrees. But call it whatever you like and start a parallel simulation. So now in the job status down the bottom, you should be able to see that you've got 2 simulations being run. And those simulation jobs will be conducted in parallel, and you'll be able to analyze the results once they're complete. Okay, but For the sake of the workshop, we obviously don't need to wait for those simulations to complete. We've prepared a couple of simulations to post-process in advance. So you might want to collapse some of your milestones on the left-hand side so that we can see where we are. And we're going to be using these two, milestone 7 and milestone 8. So let's start with milestone 7. If you scroll to the bottom, you'll be able to see one of the completed simulation runs that has been run in advance for you. CHD, Windows open, 20 degrees. We can see that it took 110 minutes to run and it used 176 core hours. If you click the blue post-process results button, this will now take us to the post-processor so that we can analyze the results. If you get a prompt come up of which interface to use, choose the beta interface. It will very soon become the only post-processor. It should just take a few minutes to load the result. And I'll just pause on this screen for a minute to make sure that everybody has got to the same stage. You should have a default simulation post-process loading on the screen. And I'll take you through a couple of things that we can do here to post-process the result. So what we're viewing is a cutting plane, and we can see the cutting plane here, cutting plane 1. So let's have a look at what this cutting plane is actually doing. So it's cutting on the Z-axis, and we've specified a certain position for this cutting plane. So it's at the 1.2 meters Z height. So we can see that we're cutting through the head plane of the seated occupants. And on this cutting plane, we're plotting the temperature. So if we use the cube down the bottom here, we could orient to the top view so we can see the plan view of this cutting plane, normal to the plane. And I'm just going to turn the opacity up so all we can see is the cutting plane. I'm just going to switch off the vectors for a moment so that we can just see the temperature plot around the room. So we can see we've got a bottom limit of about 15 degrees Celsius and a top limit of about 35.5 degrees Celsius. And we can use the inspect point feature up the top here to pick out what some of these temperatures are. So we can see a darker blue at the window inlets. So that's on this cutting plane where we've got the lowest temperature, about 15 degrees Celsius air coming in the windows. And then because of the heat generation of the occupants, around the occupants we've got a temperature of about 18.5 degrees Celsius. And around the rest of the room, it's about 17.5 degrees Celsius. We can also use the bulk calculator for a cutting plane to have a look at what the minimum, average and maximum values for that specific cutting plane are. So that's a really useful feature for post-processing. The other thing that we can do here with the cutting plane is add vectors so that we can see how the air is actually flowing and the direction of the flow on the vector. So with these vectors, you can actually play around with the size and the scale of them. I like to project them onto the plane so we get only the magnitude that is projected onto the plane shown. So we can play about with the scale factor and the grid spacing of these vectors until we get an image that shows the flow nicely. And obviously this is only the flow on that plane, but we can zoom into specific areas and see where we've got flow recirculating. And on this plane, we don't get a very good understanding of what's happening because obviously we've got the diffusers and we've got the window here, but we're only seeing what's happening on a single plane. To get a better understanding of what's happening with the flow in the entire space, we could add some particle traces at the diffuser inlets. So I'll show you how to do that now. If you go to Add Filter and select Particle Trace, we can then start to add some particle traces. And then switch off the cutting plane. And then we can see our full geometry again. And we want to add these particle traces onto one of the flow inlets. So orient the geometry so that you can then zoom in to one of these diffuser inlets and then drop the crosshair for the particle trace roughly in the center of the diffuser inlet. And this gives us a standard 10 by 10 seed particle trace. And we can play around with this so that it fits nicely within the diffuser inlet. So if we use 5 by 5 and then reduce the spacing slightly, we'll be able to get this so that it fits within the actual diffuser. And then we can set from here whether we want cylinders, spheres, or comets. For this application, I think the cylinders are quite nice. And we can choose what property is actually plotted in the color of the particle trace. So in this situation, I think the velocity magnitude is quite a good color to have. So once you've set that, we can zoom out and see how that actually looks in the model. So in order to see what's actually happening, we can hide part 1, which is the fluid volume, and just check that our part color has got a opacity so that we can see through the surface of the default region. So the surface is going to be represented as a color, but we've got quite a transparent surface. So now we can see the particle trace from that diffuser inlet and where the flow is actually going in the room. So we can see some of the flow is almost immediately going out of the exhaust and the rest of it is circulating around the room. So you can get a really good appreciation of how the flow is interacting with the space by using the particle trace. With these particle traces as well, you can also animate them, so you can see an animated path of where the particle trace goes by going to Add Filter and Animation. And from Animation Type, select Particle Trace and press Play. And this will animate how the particles would be traced through the space. So this gives a really nice qualitative result. You can obviously add these particle traces to the window inlets and the other diffuser inlets as well to get a really nice qualitative view of how the flow would be within the building. Okay, so the other post-processing that I want to look at with you is actually having a look at our mean age of air in the room. So we've looked at the temperature. We can see how we can add cutting planes to analyze the temperature. And we're now seeing qualitatively how the flow works in the room. We can see that we've got quite a good flow around this table, but what does that actually mean for the mean age of air in the room? How COVID safe is this going to be? So one thing that we can do is we can go to our area average calculation that we made. So in the tree structure on the left-hand side here, open the area average and we can see the outlet average that we created. If you open outlet average, we can see all of the parameters that the outlet average has captured. And T1 is the one that we want to open for the passive scaler. So we can see in the simulation time, so we can see that it's converged on about 667 seconds. So we've got a mean age of air of about 11 minutes in the room. It's taking about 11 minutes for the passive scaler that's been introduced into the room to make its way to the exit, and this is on average. The other thing that we can do here with our solution and the passive scaler is have a look locally at the mean age of air. So if we go back to our solution fields and again use the beta interface, something we can do here is we can add a ISO volume. So this will isolate certain volumes within the simulation based on a parameter. So if you switch on that ISO volume, and we can see it starting to color the area. You may want to actually switch off that particle trace animation, or you can leave it on, but I'm going to switch it off so it's less noisy and we can see what's happening. So what have we plotted here? Well, we've plotted a volume, and the volume that we've plotted is of the passive scaler, and we're using a range for this ISO volume of between 700 seconds and the top limit, so 913.5. So what this shows us is everywhere in the room where the air is older than 700 seconds. So interestingly, we can see that we've got some pockets of air. We've got a volume of air that runs down the middle of the room as well, between the diffuser inlets. And we've got a volume of air accumulating above the windows where it's not being recirculated. So that's where the oldest air is in the room. So it's a really nice way of visualizing and picking out where that is. And obviously these ISO volumes can be combined with other things like the particle trace to build up a really nice post-processing understanding of what's happening. So that's some post-processing for you to try. Let's have a look at the other simulation that we ran. So this was the 20-degree window opening. Let's have a look at the alternative geometry. So we ran an alternative situation here where we had 40 degrees of window opening. And to get a quick answer on whether the mean age of air has actually been improved, we could have a look at the area average at the outlet and have a look at the passive scaler, and we can see that we've got a mean age of air of 673. So it's actually very similar between the 20-degree window opening and the 40-degree window opening. But we could obviously investigate that in more detail. All right, thanks for watching. I hope you've enjoyed following along, and please let us know any questions that you've got and we'd be happy to answer those.